It hugs the ground at over 800 kilometers an hour. From 2,500 kilometers away, it can hit a target within 10 meters. To seek out and destroy the enemy without a pilot. No wonder it's become the weapon of choice. Baghdad, 1991. The Tomahawk has its baptism of fire. Wave after wave of cruise missiles hit their targets.
Yes, the latest Tomahawk cruise missile to fly just over our position here.
Operation Desert Storm catapulted the Tomahawk onto the world stage. A smart flying bomb that struck with awesome precision. But the cruise missile hasn't always been the general's silver bullet. It took engineers decades to get it right. To build such a weapon, they had to overcome a series of extreme technical challenges. How do you push a 1.5-ton missile out of the ocean? Fly it at 880 kilometers an hour for 2,500 kilometers. Make it dodge enemy radar. And then home in on its target to strike with deadly accuracy.
560. Tell me when you think it's getting close.
It's getting close. It's getting close. It's getting close.
The first challenge. Firing a missile that weighs as much as a family car from a submarine underwater. With Tomahawks on board, a submarine turns from underwater weapon into global player.
The range of the weapon is considerable. The cruise missile now allows us to target the population centres for 90% of the world's population.
Action stations, action stations, action stations, TDAM engagement. All compartments, check communications, all compartments, check communications, DCHQ.
Captain FCO. Captain, the TLAM weapon system is in weapon intercept.
Today, a sub can simply fire and forget, safely hidden beneath the ocean.
Firing order will be 1, 2, 3, then 4 tubes. Salvo duration will be 6 minutes.
In the 1950s, the Navy could only fire missiles from the deck of submarines, an extremely awkward maneuver.
To meet the fourth missile type, whose mission takes it from surface to surface, we go to sea to rendezvous with the submarine.
The sub had to break cover and surface so the crew could fuel the missile and assemble launch equipment, leaving the sub exposed and vulnerable. The Navy desperately wanted to launch while the sub was underwater. But there was a problem. Firing a missile engine in a confined space creates an explosion so violent it rips a submarine apart. Navy engineers came up with an ingenious solution. First, flush the missile out of the torpedo tube with a jet of water. Once outside, fire the missile's rocket engine, clear of the submarine.
Weapon system ready. Allow fire.
This is how they still launch the Tomahawk today.
Execute initiated. Time of launch in 5, 4, 3, 2, 1. Initiate execute. Smack's correct.
5.
Discharge correct 4 tubes. Salvo complete.
The Tomahawk's rocket booster weighs only 270 kilos, but accelerates the weapon to 80 kilometers an hour underwater.
Missile broached.
It burns for only 12 seconds, that catapults the missile 300 meters into the air.
Booster separation.
The Tomahawk's booster may look low-tech, but making this rocket engine safe enough for a submarine is a triumph of modern chemistry. Most rockets are powered by liquid fuel. Two different liquids are fed into a chamber where they ignite and drive the rocket. Powerful, but dangerous. To show the hazards of liquid fuel, Sidney Alford will replicate a German fuel recipe from World War II.
Please stop panicking if anyone is thinking of doing so. Here we go.
The two fluids simply have to touch each other to combust spontaneously.
That, I think you'll agree, is a pretty violent, indeed explosive reaction. No particularly luminous flame, but the sound alone indicates that it's very, very violent. I'm just going to wash my face slightly. I feel slightly squirted on the head. There we are.
And Sidney only used a few drops of each liquid. But the components are dangerous even before they're mixed.
Each of them is not a very nice chemical to have around in its own right. Hydrogen peroxide, if it's very concentrated, can actually detonate. If it gets spilt onto inflammable materials like cotton or paper, it tends to catch fire spontaneously, not what you want in a submarine. Hydrazine is less of a fire risk, but it is volatile, and breathing in the vapor is not good for your health. It is significantly toxic.
When the US Navy first thought about putting liquid-fueled missiles on submarines, there was an outcry.
I've been told that the submarine captains blanched at the idea. They thought it was an awful idea.
There was only one alternative: solid fuels, like gunpowder. They were safer, but far too weak to lift a large missile out of the ocean. Solid fuel needed a big boost. This challenge landed on the bench of Charles Henderson and Keith Rumble. They had to find a chemical that made solid rocket motors burn hotter and create more thrust.
We looked at additives that we could put into the solid propellant that would increase the heat of combustion. And we're going through the periodic table.
After testing many different chemical elements, they zeroed in on the ideal candidate: aluminium. When pulverized, this metal burns easily, at 2/3 the temperature of the sun. Unfortunately, the more aluminium they put into their motors, the less potent they became. Finally, Charles Henderson found a way of squeezing 20% aluminium into a rocket engine, but only theoretically. Would it work on an actual rocket? Rob O'Brien is a physicist with a passion for rockets. He'll demonstrate the explosive effect of Rumble and Henderson's formula. Rob's mounted small rocket motors upside down on electronic scales. This allows him to measure the force each one generates, a simple gunpowder motor compared to an aluminium motor.
3, 2, 1. 3, 2, 1. Ignition.
Gunpowder produces about 1 kilogram of thrust. The aluminium motor generates twice as much.
Well, in terms of a rocket motor, if you want a high thrust, you really want a high velocity exhaust. So in order to get that, you would increase your temperature of the burn. And so putting aluminium in your mixture of the fuel increases the temperature. And if you increase the temperature of the burn, you can increase your thrust quite dramatically.
Now Rob will put these motors to the ultimate test. he'll strap them to one of his rockets. First off, gunpowder. Gunpowder is so weak it doesn't even tickle the rocket. Now, the aluminium.
Seven, 6, 5, 4, 3, 2, 1, ignition.
In the 1950s, Rumble and Henderson's improved booster was a quantum leap in missile technology.
Oh, it was great. We realized that we had gotten the performance that we wanted and have perhaps exceeded it a little bit.
Oh, well done.
It's a good question as to why others hadn't thought of it, but they didn't, and we thought of it first.
Today, aluminium motors boost all kinds of rockets, from the Space Shuttle to the Tomahawk. But solid rocket engines burn out quickly. Even the biggest boosters will only last for a few minutes. So how can a Tomahawk fly over 2,000 kilometers on a single tank of fuel?
Weapon system ready. Allow fire. Discharge correct foretube. Salvo complete.
Missile broached.
As it breaks out of the water, the Tomahawk starts an amazing transformation. Four fins grow from its tail, and an air scoop drops down in front of them. A pair of wings flip out like switchblades. The missile jettisons the booster and speeds away at 880 kilometers per hour. Within seconds, the Tomahawk has mutated from a rocket into an aircraft, which is just how the cruise missile started out. In World War I, artillery was the weapon of choice, but the furthest a gun could shoot was 30 kilometers. Aeroplanes could reach deeper into enemy territory, but they had one weakness. With no accurate bomb sight, early planes had to fly so low they became targets for enemy guns. In 1917, a crack team of engineers gathered in Dayton, Ohio to tackle this problem. Their vision was an aerial torpedo, an aircraft with the pilot removed and a bomb in his place. Inventing genius Charles Kettering would lead the team. Elmer Sperry would build the navigation system, and Orville Wright would design the airframe. The very man who'd put humans in aeroplanes would now be taking them out again. The result, the Liberty Eagle, quickly nicknamed Kettering Bug. It was a cheap and disposable aircraft, assembled out of a box in 4 minutes, using only a screwdriver and a wrench. But hidden inside was 80 kilos of high explosive.
It's quaint looking, but this quaintness is also tied to a bomb that will kill. So it's technology that looks cute, it looks like a toy. They call it the Kettering Bug, which is a cute name, but in reality it's a weapon of war designed to destroy an enemy's capacity to fight. The plan is to send hundreds of these things, maybe thousands of them, for very specific targets that are deep behind enemy lines that are far beyond what artillery can reach and are too dangerous for a pilot to take his bomber or his fighter back in that area.
The first flight tests were a series of comical errors. But then, after weeks of crashes, the Kettering Bug became the world's first cruise missile in 1918. People had been flying for only 15 years, and here was an aircraft that flew without a pilot. It had an autopilot, invented by mechanical genius Elmer Sperry. The heart of his machine was a gyroscope, a fast-spinning disc that stayed stable even while the aircraft was in motion. Connected to the steering with pneumatic pipes, the gyro was supposed to make the Bug fly in a straight line. That was the theory. Mike Francis is a world champion model glider pilot. He builds his own high-performance gliders out of carbon fiber and launches them 300 meters in the air with a rocket motor.
1, off.
His flying skills are superb. Mike will put one of his gliders at the mercy of an autopilot. He's modified the aircraft with electronic gyros to see if they can keep it straight.
The gyro will actually move the surfaces in response to any movement in the model, automatically. I'm now rolling the model, and you can see the ailerons moving up and down. If I move the model in pitch, you can see the elevator going at the back. I'm not moving the sticks. It's scary, actually. When I'm flying it, I have to look at the model, see it move, then move the stick. The gyro does that for me, far quicker than I can.
With the gyros in place, Mike should be able to launch his glider and let go of the remote.
4, 3, 2, 1, off.
I'm just about to turn the gyro on it. Now. Again, you see the model switching.
At first, the gyros do well. They keep the model steady.
You can hear the servos.
But soon the wind pushes too hard. After 10 seconds on the gyros, the glider rides out and comes dangerously close to crashing. Mike has to intervene or risk losing his precious model.
I'm back in control now. The gyro simply knows what position it's in. It doesn't know where it is in space. Consequently, the model might be flying straight into a tree. The gyros haven't got a clue that the tree's actually there. I do because I can see it. All the gyros can possibly do is keep the model straight and level.
Gyroscopes have one big problem. They drift over time. The gyros in the Kettering Bug were no exception. They had trouble keeping it on course.
They brought dignitaries from Washington, D.C. to Dayton, Ohio to show it off. And it takes off, but it keeps flying. And instead of flying straight for about 1.5 miles like they wanted it to fly, it ends up veering off and starts flying around toward the city of Dayton. Well, this is a top secret weapon. They don't want anybody to know about it, so they all jump in their cars and they start chasing after this thing as it's buzzing along at 50 miles an hour, which trying to chase down country roads around Dayton in 1917 must have been very interesting. It finally goes out and it runs out of gas and it crashes into a farmer's field. And the farmer comes out, oh, an airplane just crashed out here, but I can't find the pilot. Well, to maintain the secret, they grabbed a flying suit from the back of one of the cars and said, well, here's the pilot. He jumped out with a parachute. Well, they didn't have parachutes for airplanes at that time. But The farmer believed him, and they kept the secret.
Building the Kettering bug had taught missile designers valuable lessons. But in the end, the grandfather of the Tomahawk never saw battle. By changing from rocket to plane, the Tomahawk increases its range massively. It drops its burnt-out rocket booster and fires up a jet engine that can fly it for 2,500 kilometers on a single tank of fuel. In the 1950s, such an engine was unthinkable. Jet engines were huge gas guzzlers. Cruise missiles were enormous, far too big for a submarine. What missile builders needed was a miniature jet engine. It takes precision to build even a big jet engine. Making them smaller and more precise would be a tall order. In 1964, the solution came from an unlikely place. The US Army had been looking for a way to fly a soldier to the battlefield. Fast-burning rocket technology had failed. Enter the jet belt.
Of course, the concept started with a rocket belt, but you only had about 20 seconds of life. So then the thought was get an air-breathing engine, which will take less fuel, so you could get, with a given amount of weight, you could get much more flight time. But there was a real question about whether you could design an engine this small. It was thought probably you couldn't.
The engineers at Williams International put their heads together.
So the challenge we had was to take an engine actually a little bit larger than this, consisting of about 6,000 parts, and compress it down into a very much smaller part count.
One trick Williams used was to build highly complex parts, like turbine rotors, out of a single piece of metal. They radically simplified every component till they had an engine with only 600 parts. Weighing in at only 30 kilos, it was small enough to fit on a man's back.
It's pretty exhilarating. It's almost like somebody grabbed me by the seat of the pants and just lifted me up. It's pretty interesting.
I watched Bob fly it. He had very precise altitude control. He flew it in front of our building at one time where we had a big tree and it was in the fall, and he could point to some leaf he was going to pick up. And he did fly up in the tree. This tree was like 60 feet tall. And he went over and picked a leaf off.
The jet belt spawned a series of prototypes looking more like James Bond than G.I. Joe. But the military lost interest in these magnificent machines. Maybe they realized that on a battlefield, flying soldiers could easily become sitting ducks. The jet belt never took off commercially, but left one important legacy. Its small jet engine was a gift to missile builders. Now they had the technology to make missiles small enough for submarines, yet so powerful they could fly hundreds of kilometers. Once a Tomahawk enters the cruise phase, it starts seeking out its target. The hunt begins. As the Tomahawk cruises towards the enemy coast, it faces the ultimate challenge, flying hundreds of kilometers without getting lost. Navigation's always been the biggest headache for missile designers, especially during the Cold War, when the targets for US missiles were on the other side of the planet, over 8,000 kilometers away. Over such distances, a tiny error could add up to a big miss. Accuracy seemed impossible without a pilot. In 1946, aeronautical engineers designed a missile to end the dreaded navigational problem forever. They called it the Snark. This is one of the last remaining Snarks in the world, restored to former glory by the US Air Force. Weapons technician Jim Oskins used to maintain these missiles.
Oh, boosters and all. Cool.
He's not been near a Snark for years.
It's nice to see the old girl in one piece again. Yep, she's pretty nice. It was an extremely ambitious project, considering they were using 1950s technology in the guidance system.
The Snark featured a radically new guidance system, which used an ancient navigation aid, the stars. Using a telescope, the missile would track the position of a single star right above its flight path. Once it had locked onto it, the missile found its exact bearing and could correct course. Nice idea, but Snark was plagued by failures.
What happened with the one I saw was one booster fired and the other one didn't. It got off the launcher, but it just went into the beach. A lot of smoke, a lot of flame, and a lot of people running. Nobody was hurt, fortunately. We were not impressed, I might add.
Star navigation worked in the laboratory, but not on a missile bouncing through the air at 1,000 kilometers per hour.
This was one of the first missiles they ever tried to launch out of Cape Canaveral. And since the guidance system was very, very unusual at the time, very, very experimental, they had a lot of failures. And most of them ended up in the ocean right off the coast of Cape Canaveral. So there was a joke going around, they called it snark-infested waters. Instead, which was true. There was no stretch of the imagination there. It was true. There were a lot of them out there.
The Snark was a fantastic failure. The stars were not the answer.
Solution of the problems involved in long-range missiles would need the cooperation of more branches of science than any other project in history.
Missile designers kept looking for the elusive navigation aid. A team led by Walter Hess found it while dreaming up a truly apocalyptic missile.
Supersonic low-altitude missile, SLAM.
It was the most interesting project I ever worked on. It had all the glamour of being an immensely destructive weapon system. It was a wonderful project.
A nuclear-powered missile which would be boosted with solid...
SLAM was designed to fly into the Soviet Union at 3 times the speed of sound and wreak havoc.
It had 16 1-megaton warheads, and it would go to 16 different addresses, ejecting those warheads upward like a seed ejection mechanism, and it would fly so fast that by the time they exploded, it would be out of harm's way. The missile literally glows red because the temperature of the skin and stagnation temperature is over 1,000 degrees Fahrenheit. The shock wave of this massive missile at that high speed at near the ground has a huge effect. All normal buildings that we know would just be knocked over.
But how could a speeding missile navigate between 16 targets many kilometers apart?
One of our guys, Bill Hallmark, came up with the idea that every piece of ground has got a unique fingerprint.
Using topographic maps, Bill Hallmark and his team translated the valleys and ridges of the landscape into a digital map and uploaded it into SLAM's computer. They called their invention Fingerprint. SLAM would bounce a radar beam off the terrain it was flying over and compare it to the map stored in its memory. This is how it would zero in on its targets.
Well, we had a configuration of 50 missiles attacking simultaneously the Russian continent. And then each one, of course, would carry 16 weapons. That's 800 1-megaton warheads. You'd literally destroy Russia. In the end, the State Department determined that this would be so upsetting in the balance of terror, it was thought to be wise not to deploy the weapon system. It would just escalate the balance of power one more notch upward. And maybe Russia, thinking this system would come on, would want to deploy some of their missiles before we had it.
The USA killed the SLAM project in 1964 and put the fingerprint technology on the shelf. But when work began on the Tomahawk in the 1970s, it was rediscovered and transplanted into this missile, where it works to this day. Radar navigation gives the missile another amazing feature: stealth. As the Tomahawk reaches the coast, it drops down to evade enemy radar. Hugging the landscape tightly, it speeds along at over 800 kilometers an hour, just meters from the ground. It's a truly amazing feat of flying, and all without a pilot. Some would even say no human could possibly match the skill of a cruise missile. The radar navigation in a cruise missile never tires, but has one weakness. It needs geographic features to lock onto. That's why the cruise missiles in Desert Storm didn't attack Baghdad head-on. US mission planners feared their Tomahawks would get lost over the flat and featureless deserts of Iraq. So instead, they flew them the long way round, over the Zagros Mountains of Iran. Once a Tomahawk zeroes in on its target, it'll strike with extreme precision. But how does it know when to attack? In 1944, an unknown flying object attacked London. Mysteriously, it seemed to know exactly when it reached the city and just fell out of the sky. The German V1, the so-called buzz bomb.
London is doomed, said Dr. Goebbels. And Adolf Hitler...
Designed to terrorize Britain. While Londoners wondered what had hit them, an American officer was busy finding out. Hap Arnold had worked on the Kettering Bug, the world's first cruise missile, built 26 years earlier.
Hap Arnold went to London right after the D-Day invasion, and while he's staying on the suburbs in a house on the southwest part of London, about 5:30 in the morning, the first buzz bombs come over, and he's awakened by them going off, and they're hitting about 1.5 miles from where he's staying. Later in the day, he takes the opportunity to go out and actually visit one of these buzz bomb sites. And he goes to the thing, he sees the bits and pieces, and he quickly understands they've taken a bomb and stuck it on the front of some sort of an aircraft.
The tangled wreckage harbored important clues on how this amazing weapon found its target. Hap Arnold collected all the pieces he could find and shipped them back to America.
This is the fuel tank section, right, Joe? Correct. This is what Hap Arnold would have seen, is bits and pieces like this. Actually, he even talks about seeing bits of the nose cone and the wings were pretty much gone, but the tail surface was still available to him. A number were actually captured fairly intact if the bomb didn't go off inside. So this one looks like it hit the ground pretty hard, but not hard enough to set off the bomb. It's always bigger than it looks in the pictures, isn't it?
Yes, it is. With that big dent in the top of it, too.
I guess it hit the ground hard?
Yeah.
From battered parts like these, American engineers began to reverse engineer Hitler's secret weapon. 3 weeks later, they cracked it. The V1 had a simple yet powerful jet engine which accelerated it to an incredible 640 kilometers an hour. But the most important riddle the Americans solved was how the V1 knew when to drop. A propeller at the tip of the missile turned as it moved through the air. Each revolution was counted by a mileometer in the tail section. At a preset mileage, a guillotine cut the pneumatic hoses to the rudder, locking it in position. 2 detonators then ejected a set of spoilers, disrupting the airflow under the elevators and sending the V1 into a steep dive. Nicknamed the Doodlebug, the V1 was only accurate enough to hit a city the size of London. Good enough for the Germans.
Robot bombs damaged or destroyed 800,000 English buildings in 6 weeks. Over 1 million people have been evacuated from the city of London.
The V1 had to be stopped.
The Doodlebug is coming in at 440 miles an hour, which meant that and the Spitfire would only do about 350 miles an hour, I suppose, the maximum. So you would come in at 10,000 feet, and in a screaming dive, you would be brought down, and the radar would bring you down right onto the Doodlebug. So you're coming in, you can say it like that, and actually you would overtake the Doodlebug on the inside by about 100 miles an hour.
The pilots only had a split second to shoot. If they got it wrong, they were in trouble.
I was stupid enough to come in dead astern and open fire on the thing when I was absolutely dead astern, and the thing blew up and made an awful mess of the Spitfire. So one never did that again. You learnt that very quickly.
Terry Spencer tried another angle of attack.
I was intrigued as to whether there was a pilot in the thing or not, or what was flying these things. So I get about 2 feet in and 2 feet below the wing, and I noticed that as soon as I turned the Spitfire up like that, we would find out later on, it toppled the gyro, and then the thing just spun straight in.
The papers lapped up the story. They nicknamed Terry Spencer Tip-em-up Terry, the man who'd destroyed a V1 with a flick of his wing.
Dramatic films of the guns in action at the height of the terror, spectacular pictures.
Within a few weeks, British defences got the better of the V1.
There it is, the flying bomb.
Over half the 8,000 bombs that reached Britain were brought down. The Germans eventually abandoned the weapon. Not so the Americans.
Mass production of robot bombs in American factories, an adaptation of the German V1.
American engineers tried to turn the V1 into a high-precision weapon. To no avail.
From the launching platform, a robot goes whizzing.
The American robot bombs still missed their targets by over 12 kilometers. The modern Tomahawk is 1,000 times more accurate. First, it takes a picture of the target area and compares it to a digital photo in its computer memory. Then a GPS signal guides the missile into the target. Once locked on, a Tomahawk hits within an accuracy of 10 meters. Some say it could even fly through a window. But what if a target is invisible and sheltered beneath meters of earth and armoured concrete? Cruise missiles are extremely accurate, but have one serious problem: hardened targets. A Tomahawk is designed to be stealthy and light, and therefore only carries 500 kilos of explosives. That won't do the job if the target's a deeply buried military bunker, as Sidney Alford will demonstrate. Using a scale model, he simulates a missile attack on a bunker built into rock.
In it, I propose to place an array consisting of a military truck and some little chaps.
Sidney's detonator mimics a direct missile strike on the surface of the bunker.
Firing! 4, 3, 2, 1.
A tomahawk exploding on the bunker's surface is no more than a pinprick.
Crucial point now is what's happened inside the tunnel. And a little bit of dust has fallen off the roof of the tunnel, but apart from that, everyone's standing up in their action positions. How good as new. Since this detonator stroke bomb exploded in air on the surface, there was nothing confining the pressure, so the extremely high pressure of the gases generated by the bomb could simply dissipate in the surrounding air. They gave up their energy in the form of a shock wave, which is what you heard. You heard quite a loud bang.
To pack more punch, a cruise missile needs a bunker-busting warhead filled with heavy metal. As the heavy warhead pushes the missile deep into the bunker, a smart fuse detects what kind of material it's travelling through. Once it reaches the air of the bunker, the warhead detonates. Now Sydney simulates what a bunker-busting missile can do.
Here's a very similar block of desert to the previous one. This time, however, we assume that the incoming missile was able to penetrate into the rock a substantial distance.
This time, Sydney's so confident, he only uses half as much explosive.
Firing! 4, 3, 2, 1. Well, you can see this is clearly a very different effect. First of all, on the surface, I can see no damage at all. If we look here, we can see obvious damage. The tunnel has been almost completely voided. Here's the vehicle in significantly blown up. Chassis ripped, the top's all gone. The little men, can't see any little men. With the first bang, we had a charge that was not confined. The energy could dissipate into the surrounding air. Whereas with this one, the bomb, or the warhead, was completely surrounded by pretty incompressible plaster, corresponding to a mass of rock. Remember that we used only half as much explosive for the second bang. The only way that that compressed gas could get out was by crushing its way through the roof of the bunker, with devastating effects on the contents of the bunker, which we see.
A bunker-busting warhead can penetrate 30 meters into earth and 6 meters into concrete. Now there truly is no place to hide.
Once before, you could be fairly sure that if you were far enough behind your own lines and you were in a well-protected bunker, you didn't have to worry about being attacked by an individual aircraft. You felt fairly secure. Now, at any moment, a cruise missile can literally come through the window or come down the air duct and kill you.
The cruise missile's come a long way from its humble beginnings. But will it ever be intelligent enough to do the job of a human pilot? In the first Gulf War, aircraft flew low-level missions alongside cruise missiles. In the second, this risky job was done more and more by machines. The next-generation fighter aircraft, the Joint Strike Fighter, may be the last one ever flown by a pilot. But even the smartest weapon makes mistakes.
The Pentagon said this was a chemical and biological weapons plant. It looked, smelt and appeared to be an innocent factory to produce baby milk formula.
A cruise missile relies blindly on intelligence data, which can be wrong.
The cruise missile, once you've taken the decision to launch it, then it might be a significant amount of time before it hits its target. You might want to change your mind, but with most cruise missiles these days, you don't have that option. With a manned aircraft and a pilot, you can launch on a mission And if the situation in the target area does not meet your brief, then you can not drop, you can come back, and you can go another day.
But there's a new kind of weapon on the scene. The futuristic cousin of the cruise missile, the unmanned aerial vehicle. UAVs are more accurate than cruise missiles, and they can come back. They fly more than just one type of mission. The Predator, its skin covered in bulletproof Kevlar, its unusual shape making it nearly invisible to radar. Its cameras, so sensitive they can tell if a man on the ground is armed or not. The CIA uses Predator to take out snipers on rooftops or terrorists in hideouts. Most amazingly, this Predator could patrol the deserts of Iraq, but be controlled via satellite link by a 4-man crew sitting in an air-conditioned room in Las Vegas. The more dangerous the machines become, the more they need human guidance.